In this video I shall be looking again at a few more interesting methods of data compression. As it so happens, whenever I try to work on techniques for information coding, well, it's certainly made progress there, but I also inadvertently end up discovering methods or ways for compressing data because they are very, very related to each other. This one can be considered as some kind of a counter up or a counter down coding, where in certain the objective is to code a number which lies between m is equal to 2 power l dash as a number which lies between s, which is equal to 2 power l. So the mapping is basically from a 2 power, where l dash is much larger than l. So the mapping is basically from 2 power l dash to 2 power l. The first interesting method of coding is based on the observation of the following fact. First is the sequences first one is 1 by 2 minus x, comma 1 by 4 minus 2x, comma 1 by 8 minus 4x, comma, and so on, 1 by 16 minus 8x, and so on. This sequence has also the other side of it, which is 1 by 2 plus x, comma 1 by 4 plus 2x, comma 1 by 8 plus 4x, comma, and so on. These two sequences have the same property, as 1 by 2, comma 1 by 4, 1 by 8, and so on. So clearly you can see that on the face of it, it appears as though the redistribution of weights cannot be done while still maintaining that property as invariant. But these two sequences, interestingly, have this property that they tend to maintain the invariant much the same way as this. Okay? So this fact, the fact that, let us take one of those things to code a slightly larger number, which of course will be slightly less than 1 by, and the last ratio must be 1 by 2, 2 power l dash. Therefore we have here, right, so we can let's just take the case of the first one, which is 1 by 2 minus x, comma 1 by 4 minus 2x, comma 1 by 8 minus 4x, and so on. We need L ratios of this. There are L dash ratios. M has the sequence of ratios for M will be 1 by 2, 1 by 4, and so on up to 1 by 2 power L. So this the two sequences are 1 by 2 minus x, 1 by 4, and so on up to 1 by, we require only L of these instead of L dash. Here it should be 2 power L minus 2 power L minus 1 into x. Likewise, we have the other sequence as well. 1 by 2 plus x, comma 1 by 4 plus 2x, comma 1 by 8 plus 4x, comma 1 by 2, here we require 1 by 2 power L plus 2 power L minus 1 into x. So we can, if we take this one as a, we can find the value of x here as 1 by 2 power L plus 2 power L minus 1 into x is equal to 1 by 2 power L dash, or 2 power L dash equal to 2 power L minus 1 times 2 plus x, or x is equal to 2 power L dash minus L plus 1 minus 2. So this is the value of x which you can use. So you will be able to code a fairly close value up to 2 power L dash with this. So you can just have to meet a precede it with a counter, so that you know within which range it lies of m, which will not be, which can be not be comparative to the size of the information. This will be very, very small, which is the size of the code. So this can be used basically for, ideally it can be used for video or audio coding. So it's basically losslessly coding audio and video. This is for so very, very compared to the size of the information, the size of the data here, coded information will be very, very small and compact, and it will also be lossless. And this, now again we'll look at another method which was also along similar lines. Three methods, which are two or three. Two of them are very are all right. The third one is not, may not be as, I was not too pleased with that. But again, this another method which can be used. I don't know what to call. This is basically again based on the similar thought or similar idea only. The objective is to code a number which is from 2 power L dash m to a value within S, which is 2 power L, where L dash is significantly larger than L. So the ratios associated again with the L dash values of m are 1 by 2, 1 by 4, 1 by 8, and so on up to 1 by 2 power L dash. So here there are L dash terms here of m, for m. So now our objective, likewise we will have a similar thing for S, but now we have 1 by 2. These ratios are from left to right of the bits of m and S respectively, and so on. However, the first ratio should be half and the last ratio should be 1 by 2 power L dash, and there must be in all total only L terms. So these L minus 2 terms of are all blanks. So we have to fill them up with ratios such that sum of all these ratios, the two criteria, the blanks must be filled up with ratios satisfying the following two criteria. So the first criteria is the sum of the ratios must add up to add up to 1, and the second criteria is the value of the ith ratio must be ever so slightly more than the sum of all the ratios preceding it. So these two criteria must be satisfied when you try to fill up those blanks with ratios. Okay. Now we make use of so we try to fill up those L minus 2 blank ratios. Let's call those ratios from right to left. So we have here, so from right to left as R1, R2 and so on up to R L minus 2. This is preceded by 1 by 2 power L dash here, and this is succeeded by that, preceded by that, and this is succeeded by, even though it comes here, it is a higher value. Okay, so we start from right to left here. So what we require initially is that R2 minus R1, or rather, let's take this way, R1 minus R2 power L dash, we require R1 minus 1 by 2 power L dash is equal to half of R2 minus R1, which upon simplification yields R1 is equal to R2 by 3 plus 1 by 3 into 2 power L dash minus 1. Okay. In a similar fashion, we can assume R1 minus 1 by 2 power L dash is equal to 1 by 4 times R3 minus R2, which gives R2 is equal to R3 by 4 plus 1 by 2 power L dash minus 1 by 3 into 2 power L dash minus 1, or upon simplification, this gives you 3 by 7 times R3 plus 1 by 7 times 2 power L dash minus 2. We are expressing R2 R R1 in terms of R2, R2 in terms of R3, R3 in terms of R4, and so on. Finally, we'll come up with half here because we know what that value is. We can substitute it and reverse, get all the other ratios there which satisfy this. Right? In a similar fashion, we also need, you'll have to do a bit of back substitution here. If a certain pattern emerges in the values of R3, I think it certainly does, which it certainly does because it seems to add up a power and a power of 2 minus 1. So you should be able to obtain the ratios. Similarly, we require again R1 minus 1 by 2 power L dash is equal to 1 by 8 times R4 minus R3, performing two substitutions here, replacing R1 with R2, which expresses in terms of R3. So first replacing R1, expressing R1 in terms of R2, then expressing R2 in terms of R3, and transferring the terms again and performing the substitution, we obtain the final value that I get is something like this. R3 is equal to 7 by 15 times R4 plus 11 by 5 times 2 power L dash. So this. So as you can see, like this you can obtain all those ratios as well, which maintain that particular property. So this is another method of coding. Which I came up with by trying to code the information for the sake of error detection and correction. And finally, I look at another third method. Again, all of these here, again, you're noticing that I'm making use of the invariant that, like the ratios or the weights or whatever you call it, each time the difference between is equal to the previous weight. That fact has been made use of in the previous two derivations. So, but here also similarly, now here you could try to obtain the problem again is to distribute these weights which lie between 2 power L dash to 2 power L S equal to 2 power L, where L dash is significantly larger than L. Now the idea is to start off with the least weight. So what happens here is you have WL dash minus 1 and so on up to W naught. Right, this is 1, 2, 3, this is up to 2 power L dash minus 1. What you note is W naught is WL dash minus 1 by 2 power L dash minus 1 and so on. Right? So, along the same veins, if we assume the weight, we can try and so what the idea is thinking behind this is, suppose I start off with D, then whatever is, if I have coded D as the rightmost value, the smallest weight which you can code, then I'm left with M minus D. And this must be divided by, right? So whatever is the value last here is the total maximum value, which must be distributed among these L minus 1. This is one weight. In all there are L weights. if whatever is the largest value, right? So that by 2 power L minus 1 is what should be satisfied here. Then having done that, so you have take away m minus d by 2 power L minus 1 plus d whole divided by 2 power L minus 2 and so on, must be the weights like this. You can try and distribute it this way. So d need not be too large or too small. So the number of iterations or iterations or repetitions to losslessly code as big numbers of L dash bits in a small, few very small multiples of L will be very high. In general, we can have W minus 1 equal to D and Wi equal to M minus Wi minus 1 by 2 power L minus I, where I is greater than or equal to 0, and D we can obtain as 2 power L dash minus 2 power L plus L dash by C, where C is not too large. Value of 2 is also sufficient. 2, 3, something very, very close. It need not be just an integer. Integer is also sufficient. So this way of distributing. So these are a few of the ways, methods of you can losslessly code, compress code information.